We are now at the third part of our lecture regarding inventory theory, where in the first part we treat the deterministic models, meaning that we assume that all our input factors are known with certainty, and then we abstract from uncertainty. So we have looked at examples where we can induce somewhat a kind of uncertainty that we allow for backordering. So we take into consideration that our customers may order more that we reordered, so we would encounter backordering. We assume here also that we have no loss of goodwill, meaning that our customers are not so unsatisfied with waiting for their order in the new circle that they would change to another provider. So here now you can take the following exercise. We have a convenience store, and by the way, I would invite everybody who's following to the video so far to take this challenge. We have a convenience store that has a demand for toilet paper at in this times very low rates per month. They they sell it in packages containing dozens rolls at a certain and sell it at a certain cost. So now you should assume that there is a fixed cost for placing an order, and we have or the convenience store has a holding cost rate. Now you should help the convenience store to determine the optimal order quantity and the optimal reorder interval, and together with the optimal ordering costs using the EOQ formula with backordering. Then the next question is we are allowed now, or the convenience store is allowed now to take back orders. So as described earlier, the customers are willing to wait for the next circle until they get the toilet paper. Please use now the EOQ formula with backordering to determine the entities mentioned beforehand, the optimal order quantity, and also now the maximum backlog allowed together with the optimal average annual cost, and also the fraction that we have positive in on-hand inventory as well as negative on-hand inventory, meaning the fraction of time that we encounter back orders. Now we look at another extension of the EOQ formula. We take now the simplest form for this, so we re-abstract from positive order lead times and from back ordering, but we take our simple EOQ formula, and now we want to see how our optimal terms change when we regard a positive finite production rate. If we look at our graphic again, then we assume once again that in the beginning and in the ending of the cycle we have zero inventory holding. And now you will see in the graphic that if we abstract from a finite production rate, then we would begin with an reorder, where we order Q units of a product, and then it depletes with our demand rate until it hits zero inventory. And that is our cycle that we have regarded so far. So this triangle is what we have calculated with a normal EOQ formula. Now we extend this model that we have a finite production rate. So we are looking at an internal process now of reordering. We have a production where we need to wait now until we get our items, meaning that we have a production rate that produces now the orders. Meanwhile, we take also units out of the stock while we have our finite production rate. So the production rate is producing and our inventory is building up at a rate P minus D, so the production rate minus the demand. Here we need to add that we assume that the production rate is greater than the demand rate, because we would not keep up and produce or build our stock and inventory if that would not be the case. Then if we take more out than we can produce, we would go negative, and we want to abstract from that case here. So we are building up inventory with the production rate minus the demand rate until we hit a maximal inventory holding that we denote by Qmax. So Qmax we can also write at this peak time where we stop them production as P minus D. That was the rate of building up our inventory, multiplied by D divided by T, and multiplied by T, which is the time here that we are building up inventory. Then we stop, and then we have the usual depletion rate until we hit 0. So the optimal values are first some little text that I just explained what happens. Here I want to introduce also the term rho as the Greek rho as the utilization rate that is denoted by the demand divided by the production rate, and we assume that this is smaller or equal to 1. Otherwise we would not have enough production capacity to keep up with producing while we take out demand. So at the maximum level of on-hand inventory, we have our peak that I just showed you on the graphic, and now the average inventory is this Qmax divided by 2, so that we can have the average annual cost function with respect to Q given as follows. Here we have the fixed ordering costs in our time horizon T, plus so this is our setup cost in the time horizon, plus our average inventory holding, and we know that T is Q divided D, so we can rearrange or rewrite the term here, and then we have here the term for our average inventory holding cost. If we look now at the average annual holding or inventory, not inventory cost, but sorry, the overall total cost for inventory holding and for setup costs, then we can rewrite these terms. If we use the normal, we take the total cost function, and then we want to determine the optimal cycle time and the optimal production quantity and the optimal average annual cost. We get the following terms for these, or the following expressions for these items. But for those who are unfamiliar with how to do it, I want to show you now on the whiteboard how you derive these expressions. For those who find that this is clear, of course, can skip the following. So let us now consider how our inventory level is increasing and then decreasing. So we reproduce the graphic shown in the lecture slides. We are starting with an inventory that is 0, and now we have a finite production rate that builds up inventory. Meanwhile, we take out demand out of our stocks, so we have a rate of increasing the production that is given by P, the production rate, minus the demand that we take out. Then when we have reached our maximal inventory holding that we need to define somehow, where we want to stop production, then we have this peak that we can also express as Qmax equals to our inventory holding building up in the time period denoted by D divided P multiplied by T. And this is exactly this point here. So we have this time that is given by the d divided by p and multiplied by the time. So we are looking now at the time that elapses. This is exactly the point where we reach our Qmax. This does not look, or it looks a little bit complicating with a lot of p's and our d's. So we can rearrange the terms a little bit. So we get d multiplied by t, 1 minus rho, and the Greek rho was or is defined as d divided p. So when we have reached our peak, then we stop production and we take just out the demand that we are facing. So our inventory depletes at the demand rate until the point t where our inventory hits 0. What we want to know now is how much inventory we have in our during this time until it hits 0 again, so until t, when we have to restart production at a new cycle, and then the whole cycle repeats itself in the same manner. And this is where we have continuous inventory theory. We assume that this one cycle here that we are regarding, I denote it or I highlight it. So we want to know the inventory that is given on average in this cycle. And we assume that everything stays equal for the next time periods, so that we can just repeat the cycle. So it's fine to regard just or to calculate just this one cycle, because then it will repeat itself. So we have in this time fraction of our cycle, we have P minus D of inventory that accumulates in the time interval which is given by, or starting by 0 until d divided p multiplied by t, which is our point here in time. We can now express our average inventory in our time interval from 0 to now t. So the whole triangle, not just until the peak point that was given here, but we include now the overall cycle from 0 inventory to 0 inventory in one cycle. And when we denote the average inventory as E from T, we can express it by the integral where T is the basis, T is our overall cycle length, multiplied in the area from 0 until T. This is E from T dt. And this can be then denoted with our peak formula. So we take the average inventory, and this is then d multiplied by 1 minus rho multiplied by t to quadrat. And now we can lose here 1t. And then the formula is given as 1/2 d1 minus rho multiplied T. So this is now the average inventory in our time interval. And in order to find the optimal reorder quantity and the optimal cycle length with respect to our finite production rate, here we denote, or I just denote, the average inventory holding and ordering. So the setup costs, we called them. Now we are internal, so I call it setup costs. So the average setup and inventory holding costs are then given as follows. So I do not take the purchasing into account. So C multiplied D drops out because it does not depend on the order quantity. But of course, if you want to calculate then the overall optimal average costs, you would have to take them into account. But here we abstract from them. So we denote this T, zeta from T, and now we regard this with respect to the time, not Q first. And this is then our formula from above multiplied by the inventory holding cost, H 1/2 D 1 minus, now I use not rho but D divided by P. So they are the same, but I think it's easier to see what happens if we don't use the Greek rho. And now plus the setup costs, K divided by T, and recall that our T is given by D divided Q for later on. Yeah, so after the usual differentiating this cost function from T and then setting this to 0, we get the optimal cycle length or the optimal time in between the orders as 2K divided by H multiplied by D multiplied, and this is the square root, multiplied by 1 divided 1 minus dp, or denoted rho. Yeah, and if we set, now we want also the optimal reorder quantity, so the Q star. We recall that this is D multiplied by the optimal cycle length. And if we put this term, and if we insert this, then we get the optimal reorder quantity after some algebra that is given by 2kd divided h multiplied by squared 1 divided 1 minus d divided p. And then the last term missing is the optimal average setup and inventory holding cost, so total costs. That is given by 2k dh squared multiplied by 1 minus dp, and this is also denoted as rho. Now at what happens when we have an increase in the production rate. Let's take for this purpose our graphic. let's assume now that our production rate increases, so that we are faster building up our inventory. Then we see that the time dpt, and this was our row, it decreases. So that means that we are faster building up our inventory until we hit the peak. On the other hand, when we increase row, that means, if we we say everything remains equal with this comparison, so the demand rate is equal, then the production rate would need to drop in order to decrease this ratio. So we are slower building up our inventory. Then we see that the row increases in total, and that inventory accumulates slower when our row is increasing. What would happen now if, for instance, we assume that our ratio, so row, that was defined as D divided by P, if now this would approach 1, meaning that production rate and the demand rate would be perfectly balanced. So what we are producing is demanded, so demand rate would be in balance with our production rate. What would happen in this case? That is easy to see. So we would assume that the cycle repeats itself all the time. So this would go to infinite. So we keep on going this forever, and that would mean that our average cost in this optimal cycle length would approach 0. Because we do not have inventory, we produce exactly what we take out, and so the optimal, or the balance of setup costs and holding cost would approach 0 in this case.